Hello everyone, and welcome to the official YouTube channel for the Wayne State University chapter of the Tau Beta Pi Engineering Honor Society. My name is Austin Heitzman. I am back again with another installment of our elementary linear algebra series. Today we'll be starting chapter 3, section 1, which dives into the definition of a vector space. And as you see, this is just a definition, right? So this is going to be kind of a shorter video as we just kind of like lay out the landscape a little bit. But it is going to be important as we continue this course. So without further ado, we're just going to get into the definition. The definition involves these 10 axioms, right? These 10 things that are, regarded as being established, accepted, absolutely true. And these axioms are going to kind of tell us whether some set is what we call a vector space, right? Basically, the two main things that we need to deal with, two operations. We're going to have addition, we're going to have scalar multiplication. Wow, this sounds really familiar, right? These are basically the two operations that we can perform on matrices and vectors, if you will remember from chapter 1. But the catch for a set, we'll call it V, to be a vector space, is that over these two operations, they need to satisfy these 10 axioms. I know you're thinking this 10, oh my gosh, that is a crazy number, but fear not, they all kind of flow with each other. It's not going to be that bad. So, without further ado, we're going to start looking at these axioms. I know they look scary, but again, we've seen most of this before, and the parts that we haven't seen before kind of stem pretty naturally from the other stuff, right? Just kind of scrolling to give you a preview here, and in this preview, you're going to notice that we have some kind of new notation, right? See if you can pick it out. The new notation is going to be this, right? We also see it down here with this. So I'm going to do a little sidebar, right? This and this is basically just addition. And this one is scalar multiplication. Same sign we're used to seeing, just with a little circle around it. And the reason we want to do that here is for a frankly wild reason that does not really show up anywhere else in the chapter. I mean, when my instructor went over it with my class, he pretty much introduced it and then said, okay, well, this is good for you to know, but we're not going to be using it. However, it was kind of one of those mathematical moments for me, which makes me sound really like insane, that kind of blew my mind, right? So what this circle means is that it could be standard addition, right? Like, you know how we generally do vector addition. If we have one vector is A and B and another is C and D, right? Well, generally, if we do V plus W, that's just going to be A plus C, B plus D, right? But you could also do something funny with it, right? So say that I want to introduce a space where the funny plus W, instead of it being equal to A plus C, maybe it's equal to A minus C and B minus D. Or maybe it's equal to 2A minus C and 2B minus D, so on and so forth. We can define the rules of addition. Similarly, we can define the rules of multiplication so that instead of, standard C times W is usually C, C, and CD, right? Well, instead of that, we can just say, instead of it just being CC, I can say it's 2CC, 2CD. I can say 0, 0. I can say whatever I want, right? As long as we are defining it in a very specific way. And this is crazy to me. And I know that shouldn't be all that wild, but for me, if you will allow me this tangent, I have always been under the impression that mathematics is very rigid and distinct, and the rules have already been carved out for us, right? But this right here, this is saying that we have a hand in writing those rules for specific systems, right? So I don't know, maybe that sounds silly, but I hope that at least someone is kind of have the wheels turning after that, right? So that's the end of the tangent. I basically just want to introduce that to you so that you know it exists. And like my instructor said, it's good to know that that is a possibility, and perhaps if you move on to higher linear algebra, you'll be working with it. From what I understand from my impression of this course so far, this will not be highly talked about. However, in homework questions, you might see like such that addition is defined in this way and scalar multiplication is defined in another way. So just keep an eye out for that. Yeah, that will actually change whether something is a subspace or a space, as we will be talking about here. So now that we have moved on to that, let us actually go into these 10 axioms. And I'm going to go a little out of order here, right? For now, I'm going to skip 1, and I'm going to skip 6. Because number 2 is something we've seen before, right? Number 2 is saying that in order for V to be a vector space, any of its vectors U has to be commutative with vector V, right? You've seen that before just in terms of like the rules of addition. Similarly, if we have vectors U, V, and W, when we add those vectors up, they must be associative. So grouping does not matter. Another pretty standard property of addition here is 0. And this one, put a different color star. This one's actually really important because it's going to be very helpful for you to remember that if a set is a space, a vector space, it must include a 0 vector such that 0 plus any vector is just going to equal that vector, right? That will come in handy. And also we have that identity, right? The additive identity. And this is basically going to say that for every vector U, it's going to be a negative U so that the two cancel out when you add them. So U plus negative U is equal to 0. Negative U plus U equals to 0 because, again, it's commutative. So those first 5 are going to be properties of addition. Similarly, the last 5 are going to be properties of scalar multiplication. Like I said, I'm going to skip number 6 just for a moment because I want you to understand that a lot of this is very familiar, right? Similarly to how we've seen most of the additive properties before, we've seen most of these before, right? This is nothing more than our old pal, the distributive property, right? So basically, if you take a scalar in the set V, it is distributive. It must be distributive. Similarly, if you have C plus D as scalars and you scalar multiply that with U, That's going to be the same as tearing this apart, right? Same old scenario here. If you do like a scalar times parentheses scalar times a vector, you can just multiply those scalars ahead of time. You can pull all of those out. And finally, this is the multiplicative identity. Such that 1 times any vector must equal the vector, right? So what does all of this mean? Well, if I have some set that I am given, if I want to make dang sure that it is a vector space in the complete definition of it, well, that means any of its vectors must satisfy these properties, and any of the scalars that you can possibly introduce from the real numbers, because in this course, of course, we're going to be dealing with the real numbers, that must satisfy these properties. The ones that we have just discussed, these multiplicative identity, the distributive property, additive and associative, commutative, whatever, these fall naturally out of these two that we haven't touched yet. These two that we haven't touched yet are called like closedness properties. And two exist, one for addition, and the other, which I'm going to call 6, as you'll see, for multiplication. I should say scalar multiplication, I apologize. Now for addition, all this means is that if you add any two vectors from V, the result of that must also be in the space, potential space, right? So this one is a closed under addition. And similarly, if you multiply any scalar by a vector in V, the output of that must also be in V. This is closedness, or closed under scalar multiplication. So what does this mean practically? And of course we'll do an example at the end, but I do just kind of want to give you an idea really, really quick. So say we have the vector 0, right? I'll do it as a 0 vector in R3, right? And say that very simplistically we want to prove that this is a space, vector space. Question mark? Is it? Well, we can definitely prove, right? So since all we're saying is this, that this lowly vector is its own space, this is our proposition. Well, under these properties, U and V must be in this space, right? So U is the 0 vector and V is the 0 vector. Well, is U plus V also the 0 vector? Yeah, it certainly is. Because if we add the 0 to 0, it's always going to be 0. Further, if we take any scalar and multiply it by a 0 vector, it's always going to be 0, right? The output of this is in this, right? So, yeah, we do have a vector space with 0. However, remember what we were just talking about like the funny definitions of addition, right? So say U plus V is actually u plus v, u1 plus v1, and u2 plus v2, and u3 plus v3 plus 1, right? Well, now, if we do u plus v, that is actually going to give us 0, 0. Now we have this plus 1 here, so that last cell is going to be 1. This is not in this potential space, right? Sorry about that. I don't know what happened there. So, under this definition of addition, 0 would not be a vector space. And you can manipulate multiplication in the same way if you wanted to just prove a point like this. Obviously, like a very abstract example, I guess, but I just want to give you some idea of like what it means to be closed under addition and multiplication. The output needs to be in this proposed vector space, right? Okay, so from here we have our 10 axioms, right? And in order to get used to these 10 axioms, it's going to be really important to prove each one of them for your problems. However, it's important to note that as soon as you have disproved one of these, all the rest are out the window, because immediately it is no longer even a candidate for a vector space. Right, so when you're doing these problems, when a problem says determine whether V is a vector space, or demonstrate why V is not a vector space, or why it is, right? Really, the strategy you need to go for is you look at it and you say, well, is it closed? Yeah. Is it closed under addition? Is it closed under multiplication? Is there a zero vector? Because sometimes there's not. Those things will immediately throw it out the window. Those are going to be your top 3 candidates. That's why I starred them, right? Because those are going to be the quickest to prove. However, sometimes that's a lot of guess and check, for lack of a better phrase. And sometimes it's just easier to see right off the bat that perhaps there's 2 vectors within a proposed vector space that are not commutative, for example, or not associative, or perhaps there's no additive identity, so on and so forth. You can use this as you need to, and my point is, learn it well, because if you have the whole arsenal at your disposal, you'll be better prepared to use it to your advantage, right? So, before we go on to our main example, other than that, whatever that was on the sidebar, I do just want to give a brief note about vectors, right? Because up until this point of this course, when we have said vector, we have meant some matrix with only one column. Wow, what is my writing today? I'm so sorry. Only one column, right? But now that we're talking about vector spaces, well, a vector space is not restricted to being a matrix with only one column. It could be any sort of set, right? That could be a set of 2x2 matrices. This is a common one. I'm going to call that capital M with a little 2x2 subscript. It could be another really common one we see in this chapter is the set of polynomials. This is denoted with this like fancy P. It's going to have a subscript n with the degree less than or equal to n, right? And that is important, actually. Because remember, as we start working with these polynomials, as we start breaking them down, the degrees start to reduce, right? But they're never going to go up from what we have. Similarly, like the set of like real numbers, a Euclidean space, R superscript n, shout out to, what was that, chapter 2, that can be a vector space. We can have the set of complex numbers. This little fancy C, that's a vector space, right? So I don't want you to see vector spaces and think, well, we're just working with the vectors that I'm familiar with. It's going to start to expand now. And our question becomes, how do we reconcile this? How can we say that something like this, heck, something like this, which does not really look like a vector that we're familiar with, how can we say that that can be a vector space? Well, we can convert it into a vector, right? If you missed this last time, feel free to check out a video from chapter 2, because we went over that a 2x2 matrix can just be converted to a vector like so. Really, in any size matrix, any specifically square matrix can be converted into a vector like that, right? Heck, not even a square matrix. We can do this now. You know, we've already built the stuff to do this. Even a polynomial, actually, right? The polynomials can get a little tricky, but once you kind of start laying it out, it becomes pretty apparent, right? Because think about a vector, all that is just a line of numbers, right? All a matrix is a grid of numbers. The reason we do this is to organize them, yeah? So if we have a set of polynomials, right, well, what's going to be the common thing in polynomials? They have the variable to some power, if any, and they have the constant out front, right? That's basic stuff. Well, if we're going to organize this where we have x squared and x and the constant all in line, well, from there we have a vector, right? So we can even convert polynomials into vectors. How cool is that? And this, I just do want to mention, like, you can rearrange, like, if you want the constant on top and go ascending or descending, it does not matter. You write the rules for this, right? What really matters is consistency. So you just got to be very clear with what you're doing. You have to stick to it. So now that we have laid out all of the rules and all of the ideas, let us dive into a pretty simple example. Now, if you happen to be taking this class at Wayne State and you're going through the same textbook that we're doing, this Introduction to Linear Algebra and Applications, you'll notice that this example comes from the textbook and it's just 2 parts of like a 5-part question or something. Highly encourage you to go through and do the rest of them. I kid you not, my last quiz, I think it was like directly pulled from this. Like, this is a very quizzable and testable question, because if you can understand how to determine whether V is a vector space, you will be able to do that with any sort of sets given out, right? So, let's just get started. So for questions like these, I guess I should read the question first. So we're going to let V be the set of 2x2 matrices, and we're going to use the standard definition of addition and multiplication. We don't need any of the funny signs or whatever. No, just plus and multiplication. And our task is to determine whether V is a vector space, right? So the first one we got is the set of all upper triangular matrices. If you will remember from past courses, or chapters I should say, upper triangular matrices form a little triangle on the upper half where all of these are numbers and we got 0 at the bottom. It forms an upper triangle. So if you're first looking at a question like this, I can completely understand where you might be daunted with these prove questions, like determine whether V is a vector space is essentially saying prove that it is or prove that it isn't. And I used to be very daunted by these problems because I was thinking like, oh my gosh, so many numbers here, like how can you possibly do that? Well, we're gonna, if you haven't already gotten into the habit of generalizing by just using letters in substitute for any random number you could possibly think of, this is the time to get into the habit because it's going to make this a lot easier, right? So I am going to declare U as some 2x2 matrix within the set of all upper triangular matrices, and I'm going to determine that by making it an upper triangular matrix. The only thing I need to absolutely confirm to fit this definition is that this cell right here is going to be a 0. I don't care what any other number is. I don't even care if the other number is a 0. The only criteria is that this must be a 0. So we're going to fill the rest in with letters. Same thing, since I need to prove addition and scalar multiplication at the bare minimum, right? I'm going to need 2 vectors. So I 2x2 matrices in this case. Same deal. I need to make sure that it is within the set, because if we're not starting in the set, we're certainly not ending in the set, and at that point we're not proving anything, right? So I'm going to set that to 0, then I'm just going to continue with the letters after that. Further, I'm going to call K as the scalar. I should have done that up there, but it just tends to reduce confusion when you have like a C for some number, right? So let's start with our big 3, right? Our big 3 is going to be 1, closedness, closed addition, 2, 0 vector, 3, closed multiplication. All right, so our first question, I don't even need to draw the circle there because we've already established that this is standard addition and standard multiplication. We are wanting to determine if U plus V is also an upper triangular matrix. Well, if we're just doing a standard component addition, then U plus V, the first cell is going to be A plus D, B plus E, 0 plus 0, and C plus F, right? I do not care what these numbers are. Matters nothing to me. What I do care about is that this equals 0. 0 plus 0 in any circumstance absolutely equals 0. So this passes, right? So far, so good. Now the next thing is the 0 vector. And to determine this, all we really need to ask ourselves is the 0 form of a 2x2 matrix in V? Well, you can replace these 3 zeros with A, B, and C. As long as this is 0, yes, right? So 0 vector is in V. Lastly, we can determine whether it's closed under multiplication. We want to see if K times U is in V. You have a standard definition of scalar multiplication. So this is basically going to be Ka, Kb, K0, Kc. Don't care what these are. This equals 0? Yeah, it does. So we have proved that it is closed under addition, proved that it has a zero vector, and we've proved that it is closed under multiplication. I encourage you to actually work this out on your own, but we can say definitively that all of the other 7 axioms are implicit within these. In fact, the zero vector is technically implicit within these two. I just think it's a very handy one, honestly, to keep in your back pocket. So I like to actually work that into the routine. But we will see in the next section, actually, that this one and this one are going to be the golden tests. So at this point, we are comfortable saying, yes, V is a vector space. Now, I've only included one more of these here, and I've chosen this one because it can be a little bit tricky to actually generalize well, right? We're looking at V, where V is the set of all invertible matrices. Now, if you need a little refresher, go back to chapter 1. This is a very important concept, invertibility. So let us remind ourselves that if the determinant of A is not 0, then A is invertible. Now, this is kind of a weird thing, right? I mean, how exactly are we supposed to clearly write out A, B, C, D such that AD minus BC is not 0, and we have V that's going to be EFGH such that what EH minus FG is not equal to 0. This is very cumbersome, right? However, the fact that we know that this is the key card to invertibility, but remember how I said the zero vector comes in very much handy, right? This is why, because for a question like this, technically, I mean, we could go out and say, like, U plus V is AE, A plus E, and B plus F, and C plus G, and D plus H, and we can try to assume that this still holds, right? However, to me, at least personally, that is not quite as evident as saying, well, we need a zero vector, right? And we know that the zero vector is just 0, 0, 0, 0. But the thing is, 0 times 0 minus 0 times 0 does equal 0, which means that not in V does not include the zero vector, and we have already established this truth that any vector space must include the zero vector. Therefore, V is not a vector space. Because if one axiom is out, they are all out. They're a package deal. So, highly, highly recommend you going through and actually doing these problems. There are a couple problems in the textbook that basically ask you to go through and prove every single axiom for some set. And as much writing as that is, and as annoying as that problem was actually probably the most helpful problem in the homework because it really forces you to apply every single one of these rules. So go out there and do it. I hope this has been helpful and beneficial. I hope you got to see some cool things and get excited about this stuff because we're going to be doing a lot of it. If you find yourself needing help with some previous concepts, I do want to point out the more that I am in this class, the more I am realizing that row reduction is literally everything in linear algebra. So if you do not yet feel like you get reproduce in your sleep, I'd highly recommend you go checking out our Chapter 1 videos on this channel. We also have a bunch of other STEM class tutorial videos for things like electrical and computer engineering, mechanical engineering, other math classes, and so on and so forth. So if you like what you see here and you need some extra help, please be sure to like and subscribe. I will be back next time to talk about vector subspaces, which will expand upon this material a little bit. In the meantime, happy studying and wishing you best of luck. Bye.